It used to be that when you picked up a tool, you understood exactly how it worked just by looking at it, right?
Yeah, the mechanics were just obvious.
Exactly. You pick up a hammer, you look at the heavy metal head, you look at the wooden handle, and the physics of the tool just make perfect intuitive sense to your brain.
You can see the cause and effect.
Right. And even with early computers, I mean, as unimaginably complex as they were still just incredibly fast rule followers. You type a command, and the machine executes it exactly as written.
The mechanism was entirely visible to the programmer.
Yeah, but today, you
Hmm.
pull out your smartphone, you open an app, and suddenly you're interacting with a tool where that mechanism is completely invisible. It's hidden behind glass and code. It almost acts like it has a mind of its own.
Well, we've transitioned from tools that simply follow our explicit instructions to tools that actively anticipate our needs. And sometimes they do that before we even consciously register those needs ourselves.
Which is a little unsettling.
It is. That loss of visibility fundamentally changes our relationship with technology. I mean, we're no longer just operators. We are participants in a system we can't fully see.
Welcome to this deep dive. Today we are looking at a really comprehensive foundational source, a highly detailed Wikipedia article on machine learning. We're trying to understand how these invisible tools actually work.
And we are focusing on how we lost that visibility into our own technology.
Right. The mission today is to cut through all the relentless modern hype and buzzwords. How did we go from machines that just followed our rigid rules to these opaque black boxes that learn on their own? And, what happens when those mathematically perfect black boxes collide with our incredibly messy, biased human reality?
The collision that's happening everywhere right now.
It really is. So whether you are actively working in tech or you're just trying to navigate a world that is increasingly run by algorithms, this deep dive is going to give you the ultimate foundational map. So, okay, let's unpack this. To really understand these sophisticated algorithms running our lives right now, we have to start by tracing a massive historical paradigm shift.
The shift from programming a machine to teaching a machine.
Exactly.
And that shift actually started much earlier than most people realize. I mean, the term machine learning wasn't coined in the last decade during this current AI boom. It goes all the way back to 1959.
Wait, 1959.
Yeah. An IBM researcher named Arthur Samuel coined the term while he was working on a checkers program.
Our checkers program.
Right. He realized that manually coding every possible board state and every possible strategy into a computer was just computationally impossible. There were just too many permutations.
So what did he do?
Well, he built a program that could evaluate the board and mathematically adjust its own internal parameters based on whether it won or lost a game.
It is wild to think that the origins of the systems currently, driving our cars on the highway and diagnosing complex diseases, started with a guy trying to get a computer to calculate winning chances in a board game.
It's a very humble beginning.
And the evolution from there is just fascinating. Our source points out that by the early 1960s, the Raytheon Company had built an experimental learning machine called Cybertron.
Cybertron, yeah. That sounds incredibly sci-fi.
It really does. It analyzed complex data like sonar signals, electrocardiograms, and speech patterns using punch tape memory. But the absolute best detail here is that the machine was equipped with a literal physical goof button.
I love the goof button. A human operator would literally sit at the console and act as the teacher.
Just waiting for it to mess up.
Exactly. Whenever the machine made an incorrect decision in its pattern recognition, the human operator would physically slam the goof button. Hitting that button forced the machine to mathematically penalize the logic path it had just used, so it had to reevaluate its approach.
That is amazing. It's a highly rudimentary, tactile form of reinforcement learning.
Yeah, instead of giving the computer a strict step-by-step logical flowchart, which is, how traditional programming works, the human operator was just evaluating the final output.
If the machine's output was wrong, you hit the button. It's like traditional programming is like giving a computer a strict recipe to bake a cake.
Right.
But machine learning is like feeding the computer 100 different cakes and asking it to figure out the recipe itself, with the human occasionally slamming the goof button when it bakes something awful.
That's a great way to look at it. And what's fascinating here is the underlying philosophy of this shift, which really began to accelerate and take over the industry in the 1990s.
The shift away from logic-based AI.
Exactly. For a long time, artificial intelligence was dominated by a symbolic, logic-based approach. Researchers trying to program human knowledge and rigid cognitive rules into the machine.
Like endless lists of ifs and statements.
Yeah, but the real world is incredibly complex and noisy. You simply cannot write enough if-then statements to cover, say, every possible lighting condition a self-driving car might encounter on a rainy night.
The physical world is just too messy for a perfect set of written rules.
So the field pivoted. They embraced a concept proposed much earlier by the mathematician Alan Turing.
Right, the Turing test guy.
Him, yeah. He suggested we stop asking the philosophical, unanswerable question, can machines think? And replace it with a pragmatic, testable question, which is, can machines do what we, as thinking entities, can do?
Just focus on the output.
Yes. The focus moved entirely away from trying to replicate human consciousness or cognitive thought. Instead, the goal became achieving practical, solvable tasks based purely on statistics, probability, and optimization.
Okay, so if we are no longer writing rigid rules, how do we actually set up the classroom for the machine today? Like, how do we feed it the cakes?
Well, modern machine learning generally falls into three main paradigms based on how the data is presented to the algorithm.
Let's walk through those. The first is supervised learning, right?
Yeah, supervised learning. This is where the machine is given a data set that has already been explicitly labeled by a human teacher. You provide the system with thousands, or maybe millions, of input-output pairs.
Like classifying emails into a spam folder.
Exactly. The algorithm's job is to calculate the mathematical function that best maps those specific inputs to the correct outputs. And it's used heavily for classification, but also for something called regression analysis.
Regression is a bit different, right?
Yeah, in regression, the output isn't a category like spam or not spam. It's a continuous numerical value. For example, predicting future temperature fluctuations based on historical atmospheric data.
Oh, okay. So the machine calculates the mathematical trajectory based on the labeled history.
You got it.
Then you have the second paradigm, which is unsupervised learning. This is where the training wheels completely come off. The machine is fed a massive pile of unlabeled, raw data, and it is left completely on its own to find hidden structures or commonalities.
Right, no labels to guide it at all. So the algorithm relies on mathematical techniques like dimensionality reduction.
Dimensionality reduction. That sounds intense.
It's just a way of dealing with massive data sets. It works by mapping data points in a high-dimensional space to find which variables correlate the most. It essentially merges redundant features.
So if you have a data set with 1,000 variables,
The machine figures out which handful of variables actually drive the variance. It strips away the noise so it can process the true signal efficiently without needing a human to tell it what to look for.
okay, but here's where it gets really interesting. Because if I dump a million unlabeled data points into an algorithm and it groups them based on its own math, how does the machine know the pattern it found is actually useful?
What do you mean?
Well, what if it just groups all the photos in a database that happen to have exactly 42 red pixels in the top left corner? I mean, that is a mathematically valid pattern, but it's a completely random, meaningless coincidence in the real world.
That is a very real, very crucial tension in the field, and it's exactly why we have to distinguish between data mining and machine learning.
Okay, what's the difference?
Data mining is exploratory. It's looking for previously unknown properties or, as you said, random coincidences in a static database. Machine learning, however, is intensely focused on prediction.
It has to actually work going forward.
Yes. To ensure a pattern isn't just a meaningless coincidence like your 42 red pixels, we test the model through a concept called generalization.
Generalization, so testing it against reality.
Exactly. The true test of an algorithm isn't how well it memorizes its training data. I mean, memorization is computationally easy. Generalization is the machine's ability to apply the patterns it found to completely new, unseen examples.
Oh, I see. So if its weird red pixel rule fails to predict anything useful when exposed to new photos.
The model's internal math is penalized, and it adjusts to discard that useless rule.
It has to survive outside the classroom. Which leads us organically to the third paradigm, reinforcement learning.
Right. This is where the program interacts directly with a dynamic environment to achieve a goal.
So it's not given a static data set to analyze it all.
No, it's given a world state and a set of possible actions. As it takes actions, it receives feedback from the environment in the form of numerical rewards or punishments.
Kind of like the goof button again, but automated.
Very much so. Its sole objective is to maximize that cumulative reward over time. This is how DeepMind's AlphaGo system famously mastered the board game. Go back in 2016.
It didn't just study historical human games, right?
Right. It played millions of matches against itself, constantly tweaking its mathematical strategy to maximize the reward function of winning.
Okay, so once the machine extracts these generalized patterns from the environment, whether that's supervised, unsupervised, or reinforcement learning, how is that knowledge physically structured inside the model?
That's the big question.
Because if it isn't a list of if-then rules like old programming, what does the resulting model actually look like under the hood?
Well, the dominant architecture driving today's advancements is the artificial neural network.
EAN.
Right. These are loosely modeled on the biological structure of animal brains. So instead of traditional lines of sequential code, you have a vast web of nodes, which act as artificial neurons arranged in multiple layers.
And these nodes are connected by edges.
Yes, edges, which function like biological synapses.
And the magic really happens in those connections, doesn't it? Every single edge has a specific mathematical weight assigned to it.
Exactly. As the machine learns, it uses a process called backpropagation.
Backpropagation.
Yeah, so when the network makes an error, the mathematical difference between its guess and the correct answer is calculated. That error signal is then propagated backward through the entire network.
Like a ripple effect.
Exactly. The system automatically adjusts the weights of all those connections, strengthening some and weakening others, to minimize the error next time. So the knowledge of the system doesn't live in any single line of code. It is distributed across millions or billions of these highly specific weighted probabilities.
Wow. And our sources draw a parallel here that fundamentally changes how you look at artificial intelligence. It states that machine learning is deeply, intimately tied to data compression.
The AIXI theory.
Yes. This theoretical framework suggests that the absolute best compression of a data file is simply the smallest possible software program that can mathematically generate that file.
It is a brilliant conceptual lens. Think of a massive large language model developed by DeepMind called Chinchilla 7DB.
What did Chinchilla do?
Well, in research tests, this AI language model actually outperformed traditional, dedicated, lossless compression tools.
Wait, a language model beat compression software?
Yes. When fed raw image data, it compressed it down to 43.4% of its original size, beating the standard PNG format.
That's insane.
And for audio, it compressed data down to 16.4%, massively outperforming the FLAC format.
So if I am grasping the magnitude of this, learning, at its core, is just the ultimate form of data compression.
It really is.
We tend to anthropomorphize AI. We imagine this expansive, almost conscious brain growing inside a server rack. But maybe it's just squishing the absolute chaos of our reality into a highly efficient, mathematically predictable ZIP file.
That's exactly what it's doing. It finds the shortest statistical path to represent a staggeringly complex world.
But if we connect this to the bigger picture, that relentless drive to perfectly compress reality is exactly what causes one of the greatest technical failures in machine learning, which is overfitting.
Yes, overfitting is when the compression goes too far.
How so?
Imagine a machine trying to draw a predictive line through a graph of scattered data points. If the model is too complex, it essentially gerrymanders its own mathematical theory.
It twists itself into knots.
Right, it draws this wildly complicated, chaotic line that perfectly touches every single outlier and anomaly in the training data. It achieves perfect compression of the past.
But the past has noise in it.
Exactly. Because it has molded itself so rigidly to the specific noise of that data set, it utterly fails when deployed against new, messy data. It has high variance, but zero predictive value.
It's like a student who memorizes the exact answers to a practice test, but because they didn't actually learn the underlying concepts, they completely bomb the real exam.
That is the perfect analogy. The model didn't learn the physics of the data. It just memorized the noise.
And when we take these highly compressed pattern matchers, especially the overfitted ones, and deploy them into the unpredictable human environment, the collisions can be spectacular.
Spectacular and sometimes very dangerous.
Yeah. The sources highlight some massive high-profile failures that really pull back the curtain on the technology's limitations. Like, take the Netflix prize.
Oh, that's a classic case study.
Right. In 2006, Netflix offered a $1 million prize to anyone who could improve their Cinematic recommendation algorithm by 10%.
$1 million just for a 10% bump.
Yeah. And a team finally won it in 2009, using this complex ensemble model. But Netflix quickly realized the model was completely useless for their actual business.
Because the algorithm was mathematically sound, but the proxy data it trained on was fundamentally flawed.
The human star ratings.
Right. Human star ratings turned out to be terrible indicators of actual viewing behavior. Users would rate acclaimed documentaries 5 stars because, they wanted to project an intellectual persona.
But their actual behavior showed they spent their weekends binge-watching reality television.
Exactly. The machine optimized for the lie, not the reality.
But the stakes are often much higher than movie recommendations, unfortunately. The source notes the 2018 incident where an Uber self-driving car failed to properly classify a pedestrian with a bicycle, which resulted in a fatal collision.
A tragedy that shows how brittle these systems can be.
It also details IBM Watson's failure to deliver reliable healthcare diagnostics despite billions of dollars invested. And it highlights language models like Microsoft's Bing Chat producing hostile, erratic responses because they couldn't mathematically handle the edge cases of human conversation.
Well, sometimes the machine just learns a functionally correct but utterly useless lesson.
What do you mean by that?
The source gives a great toy example. Imagine an image classifier trained entirely on pictures of brown horses and black cats.
Okay.
The network might optimize its weights to simply conclude that any brown patch of pixels in an image is a horse.
Oh, wow. So it didn't learn the shape or the legs or the context?
Nope, it just found a lazy statistical shortcut. Brown equals horse.
And because these are nonlinear systems evaluating pixel relationships that human eyes don't even perceive, they have massive adversarial vulnerabilities.
They really do. A researcher can change a single adversarially calculated pixel in an image, something completely invisible to you and me.
Just one pixel.
Just one. By adding a specific noise vector to the image, that tiny mathematical shift cascades through the network's weights, completely fooling the machine into misclassifying a stop sign as a speed limit sign.
That is terrifying. But wait, if we know a machine learned the brown horse shortcut, or if we know it's being fooled by specific adversarial noise, how do developers fix it? Can't a software engineer just open up the code, find the line that says brown equals horse, and just delete it?
And here we hit the terrifying core of modern artificial intelligence, the black box theory.
The black box.
The answer is no, they cannot just go in and tweak the rule, because there are no explicit rules. As we discussed with neural networks, the logic is distributed across billions of minute weight adjustments.
That's all just math.
It is a vast matrix of floating point numbers. It is so mathematically opaque that even the original coders who architected the system cannot audit the specific pattern the machine extracted.
Wait, really? The people who built the system cannot trace its logic.
They know the initial architecture and they know the data they fed it, but the specific pathway of logic for any given decision is an impenetrable black box.
That is wild.
And this opaqueness is driving a critical subfield right now called explainable AI, or XAI.
Because we urgently need systems where humans can actually decipher the prediction.
Exactly, especially in high-stakes areas like medicine. Imagine a proprietary algorithm recommending unnecessary, expensive medical tests because the company that owns it trained the model on data that subtly rewards financial incentives.
If the system is a black box, it's nearly impossible for regulators to prove that mathematical intent.
Exactly.
So if we can't audit the black box's logic, we are entirely at the mercy of the data we fed it. And historically, the data we fed it is incredibly flawed. Machine learning essentially digitizes and scales historical human behavior.
It is a pure mathematical reflection, and a stark example of this occurred in 1988 at the UK's St. George's Medical School.
What happened there?
They implemented a computer program to screen initial applicants, and the program ended up automatically denying nearly 60 qualified candidates simply because they were women or because they had non-European sounding names.
Wow. But the algorithm wasn't coded to be prejudiced, right?
Yeah, it wasn't coded with malicious intent. It was trained on the historical behavior of the human admissions staff from previous years. It found the statistical pattern in the human decisions and ruthlessly codified it into a mathematical rule.
We see this mechanical echo repeatedly. The investigative organization ProPublica found that risk assessment algorithms used in the criminal justice system falsely flagged black defendants as high risk for recidivism twice as often as white defendants, again based on historical arrest data.
It just absorbs the history.
In 2015, Google Photos' classifier tagged humans as gorillas due to massive gaps in its training data.
And language models inherently absorb these flaws too, because human language corpora contain them. When Microsoft released its Tay chatbot on Twitter, it adopted inflammatory racist language almost immediately.
Because it was learning from Twitter users.
It simply ran the statistics on the text the crowd was feeding it, optimizing for engagement based on what it saw in real time.
So the tech industry is currently attempting to address some of the data flow issues, particularly around privacy, by moving toward what is called embedded machine learning.
Right, moving to the edge.
Yeah. Instead of sending all your personal biometric or text data to a giant server in the cloud to be processed, models are being deployed directly onto edge devices, like your smartphone, your smartwatch, or local industrial sensors.
But this requires specialized hardware. I mean, a standard CPU isn't efficient enough for the massive matrix multiplication required by neural networks.
So what do they use?
Devices are now equipped with tensor processing units, or TPUs, which are microchips designed specifically to run complex AI math locally, right there in your hand, without needing an internet connection.
So what does this all mean? The push to the edge solves the latency issue, and it solves the massive privacy issue of broadcasting your life to a server farm. But if we step back and look at the fundamental mechanics, does it actually solve the bias?
That's the million-dollar question.
Right. If an algorithm requires vast amounts of human data to learn, and that data is inherently skewed by history, aren't we just building incredibly fast, highly efficient digital mirrors of our own flaws?
This raises an important question about the trade-offs of localized AI. A compounding factor in the data pipeline is the lack of diversity among the engineers curating it.
Who is actually building these systems?
Well, globally, only about 16.1% of faculty members focusing on AI are female, and the broader demographics of AI PhD graduates are similarly skewed.
So the people defining the reward functions and selecting the training sets naturally represent a very narrow slice of humanity.
Exactly. The hardware is getting exponentially better, but the baseline data remains a structural issue. The AI scientist Fei-Fei Lai summarized it perfectly when she noted, "There's nothing artificial about AI. It's inspired by people, it's created by people, and it impacts people."
That is a powerful quote.
It is. Moving to embedded machine learning secures your data privacy because your personal data never leaves your device. But it also means that the mathematically opaque, biased black box we just discussed isn't living in a remote server anymore.
It's living locally.
It is now living right in your pocket.
Wow. We have covered a massive amount of technical ground today. We traced the history from Arthur Samuel's checkers to the cybernetic goof button. We mapped the three learning paradigms, unpacked how backpropagation adjusts the microscopic weights of neural networks, and looked at how AI is essentially the ultimate zip file of reality.
That's a lot to take in.
And finally, we confronted what happens when those unauditable, overfitted models collide with our inherently flawed historical data.
It truly is a profound shift in how humans interact with computation. We are moving from tools we explicitly instruct to tools we merely influence.
I want to leave you, our listener, with a final scenario to mull over, building on the mechanics of embedded machine learning and the black box. Imagine a near future where an embedded machine learning model is running entirely locally on a life-critical wearable inside your body. Let's say a smart pacemaker.
Okay?
It uses unsupervised learning to continuously map your unique biological patterns. It monitors the minute variance in your heart rate, your stress biomarkers, your sleep cycles. Then one day, it makes a split-second, life-altering decision about how to regulate your heart during a severe medical crisis.
A completely autonomous decision.
Right. But because the neural network's logic is distributed across millions of unauditable mathematical weights, neither your doctors nor the original hardware developers can explain exactly why it made that specific choice. It saved you, or maybe it didn't, but no human can read the mathematical path it took.
It is a very unsettling reality to consider. Who is ultimately responsible for the machine when it has become an unauditable black box of you?
Exactly. Pay attention to the tools you use today, the recommendations you get, the way your phone auto-completes your thoughts, the subtle nudges from your apps. How much of your own daily reality is already being shaped by these invisible, mathematically opaque patterns?
It's something we all need to be aware of.
We started by talking about the comfort of holding a hammer, seeing exactly how the physics of the tool work. We are now living in a world where the hammer decides which nail to hit, and the math won't tell us why. Thanks for joining us on this deep dive. Stay curious.